we are given a line like this, and we're given amplitude and lambda and all the wavelengths and the trough and the crest, and we're told it was sound waves. That's not it. Here is what sound, this is a sound wave. This is a light wave. I know I was taught wrong.
Doesn't make sense.
Fishy.
Shocking.
Fishy.
All right. Sound waves work like longitudinal waves. So can I yell at you just for a second? Ready?
Yeah, go for it.
Stop it! All right. So,
I felt that right here on my chest. I felt that right
I
here.
warned you. I warned it. So what happened there is from my mouth came clumps, and the clumps went, and then behind the clumps there was the spreading. In front of the clumps was the spreading. Then the clump moved closer to you, closer and closer. Did it reach your eardrum?
It sure did.
Is that what, like, when you're
Reached my
like
chest,
listening to
my
sound,
heart.
like they have the little like notches that go up and
I
down?
guess so.
That would make sense.
Yeah, it does. So the clumping moves from my mouth to your ear. And sometimes your clumpings move from your mouth to my ear. So this is what a sound wave looks like. This is what a light wave looks like. It actually is a transverse wave, and of course sound is longitudinal. So make sure, given the choice, you know which is which.
I quit my job.
What made my voice louder? What about these waves would make it louder? Since we're on sound, what would make it louder? The thing that makes it louder is the amplitude of the wave. It's easy to see amplitude in light waves. Where does the amplitude exist in sound waves? The amplitude in light waves was the difference in the height of the wave. But where do we see that in the longitudinal waves? Yes.
So it'd just be like the little stick-looking thing gets longer?
Yeah, that's actually, because they're vibrating this way, the vibrations are going to be longer, like she was saying. So it's hard to put that on the board. So can you keep that in your mind? So for sound, amplitude, as amplitude goes up, the volume goes up. The amplitude goes up, the volume goes up. So, what about pitch? So what is that we do with inverse stand? Remember that? Inverse stand? Was that the high one? What was the first one? What was the first one? Bag. Inverse stand. Okay, inverse stand. When we had that jingle about inverse tan, what was going up in that case? It wasn't volume. You weren't loud. You weren't yelling, stop it. You weren't yelling inverse tan. What was changing? MK, what was changing?
Pitch?
Pitch. So let's talk about pitch. As pitch goes up, what is it about a wave that goes up? It is not the amplitude this time. It is frequency. So the number of wavelengths hitting a given spot goes up for pitch. So more characteristics of waves. All right. We'll end the day with another formula, and we'll combine it with this formula to actually do a problem. We can't get out of here without doing a problem. So, all right. It turns out that we're going to talk about sound waves for a while. So just today a little bit next time. This is Friday. Yay. No homework. So, all right. So the sound. We're going to talk about sound for a little bit, and then we'll jump the fence and talk about light for a little bit. Today we'll just end with this idea about sound. Sound travels different speeds, velocities in different substances. Do you think that anyone in the room next to me here heard me yell? So that tells you sound went through a substance to get to their ears. And sometimes we can hear what they're doing in there. So we know that sound by experience, it goes, we can hear it through a substance. How about underwater? Have you ever did the clap the rocks under the water?
Nope.
Is-
Cassie don't cut.
Is it louder or softer when you clap the rocks under? But
Softer.
it isn't.
It's
It's
not
like
louder,
tremendously louder. It actually hurts. You have to try that again this summer. Next time you get underwater, clap those rocks together. It sounds like, oh, I don't know what. It sounds like an explosion when you clap a couple rocks together. Right? Yeah, you can feel it. Yeah. Maybe that's why it sounds
I listen to music
louder.
underwater.
Yeah.
So anyway,
Have you done that before?
to make a long story short then, and I'm running out of room, so I'll get rid of light, since we're not studying light now. We are, but not today.
And then the bass is like right in the ears.
Alright, so sound travels faster in denser material. So actually,
also
sound travels
stops
faster through the wall than it does between me and your ear than air. That's why when you're underwater, water is more dense than air. You clap the rocks, it's very loud underwater. Sound travels very well.
But it also
Under-
stops quicker, right?
What's that?
But it also stops quicker, right?
Stops quicker? I don't know about stops in a substance. I'm
Yeah,
not sure.
it's
It would make
material.
sense.
The denser material, the faster it stops oscillating.
Yeah, maybe. It could be, Brian, I'm not sure. So sound travels faster, I know that, in denser material. We'll have to look up about its ability to stop faster. All right, so let us recognize, because of these different speeds, let's talk about sound in air. So I'm going to give you a formula for the speed of sound in air. I'm sure you've been wondering about that. The velocity of sound in air equals 331.5 plus 0.606 times t. Any guesses what t would be this time? It's not time this time. So what could it be? What's another big T thing?
Period?
It would not be period. That's a good one. Because period and time are pretty much the same. That's our 5-minute bell. What else could it be? For T in physics class.
Tension.
Tension, that's a good one, but it's wrong.
Wavelength.
No, that's lambda, as you call it.
Oh, yeah, I was gonna say.
So yeah, lambda sounds like lambda.
Temperature.
Yep, that was my next
we
guess
are
actually.
smart.
Yeah, alright. This formula only works if you're in Celsius, so we're gonna do degrees.
Oh yeah, no, but Celsius.
What's wrong with that?
Yeah, you should be asking what's wrong with Fahrenheit.
We like,
I don't know.
temperature was at home, we're
There's a lot
like,
of
oh,
things
like
in other
60,
countries,
they
right?
look at us so confused, and we're like, is that
Tell them to
bad?
start
And
with
I was like,
temperature.
I'm like,
It's
Fahrenheit,
cool if you just put in
Fahrenheit.
water.
But like,
We
they
need to go off
don't,
the
like,
physics
I
equation.
none of us
They
knew
think
how
they
to
can
word it.
Celsius. I think we ought to do that.
Brian,
Because
we don't not
Take
do
it
it.
into
Alright.
adjust.
So
So the velocity and sound in
Water
air
differences.
is indicated by that formula. It's of course it's a velocity, so we'll end up with meters per second. So, does anyone have perfect pitch?
Triple bag and inverse
Can you
temperature.
sing at a perfect pitch? Anyone?
Perfect
Anyone
pitch.
can, like if I say, can you sing the note A?
Hey, Hunter was here.
Who's got Hunter good?
Ryan's got perfect pitch.
Could you try to find it for us? A perfect A.
Ryan,
on
sing
there.
A.
Can I ask
Safari.
Siri?
you gotta sing.
Or Siri.
What do I ask? What is the
I don't
perfect
know.
A?
Ryan can, he's got perfect pitch.
Can you do A? Is that A? You think
Yeah.
it is? Never mind, we've got an A. Alright, alright. So, it's being drowned out by our lovely heat system.
Helicopter.
Alright, let me see if I can copy it. Do it again, Brian. Alright, everybody, copy it. You're messing us up. Everyone but Alex copy it. Okay, alright.
You said like Gregorian.
Alright.
Like, cut deep.
Very good, thank you, Brian. You're quite impressed.
It's so bugging right now.
It's
strong.
We're learning.
Yeah, that's it.
All right, that A that you just heard and
Snow tomorrow.
copied
Cancel the ACT.
has a
That's what I'm hoping
frequency.
for right now. Like this winter's like canceling it.
The
It is hard to count, so you
frequency
never know.
of A, remember pitch is determined by frequency, so I can
But
give
I
you the
chance
frequency
still
of
there,
A,
True.
and it's
You're in a hard county.
140.0 hertz. That is the frequency we just heard in the pitch of A.
Doesn't it depend on the temperature?
The frequency will not depend on the temperature. So
Ah.
now, you can see where I'm going with this. So let's try to get our problem in. If not, we'll stop mid-problem and pick it up on Monday. If the temperature is 25 degrees Celsius, I want you to find the wavelength. Find wavelength. So, that is our problem for today. The A frequency is given, the temperature is given, find lambda. This equation, the one with the pink circles, relates all the variables, so we'll start with that. F equals V over lambda. Which of these do we already know? Frequent lambda. The frequency is 440. I've dropped some of the sig figs, but I'll count them later. Velocity is what? Uh-oh. I need to find velocity. Where could I go on the board? Here's what we're looking for. We're looking for the wavelength. Where can I go on the board to find the velocity?
The equation.
Right. Could you tap it in? So I need velocity from here. Temperature is 25, so you put that in for T. So what is 331.5? Anyone tip tapping? 331.5 plus 0.606 times 25. Oh.
Oh, shnikey.
3,302.
How much?
346.65?
Yeah.
You got
We'll go with that.
0.606?
Oh, wait, hold on.
0.606?
At times.
I got something like 347.
That's what I
That's
got.
what I'm keeping.
347.
All right, 347. And when you solve that for
347.
lambda, the wavelength is quite long. It's like almost 0.8 of a meter, 0.78 actually. So a meter's that long. So a wavelength that you heard from Ryan and copied was this long in the air. That is a long wavelength. All right. No homework, just meditate on these things.
On that day on the ACT on this.
Come back, be ready
Yeah, I'm gonna use
to
physics
add
tomorrow.
to it.
There's all those
I'm
brain
really
questions
nervous.
in the ACT. And I'm like,
Bye.
oh. I know